Hi everyone, my name is Maddie Howe. I'm a PhD student at Monash University, as was just said. And today I'll be talking about how we can use astroseismology of evolved stars to study the multiple populations in the globular cluster M80. And it works, that's good. So I wanted to start with going back to the basics and give basically a glossary of what I mean by evolved stars and globular clusters, maybe to those galaxy people out there. So when I'm talking about a typical globular cluster star, these stars are old, so they have ages similar to the age of the universe. They're metal poor, so have a metallicity less than solar, and they're low mass, so 1 solar mass or less. And evolved stars, which I also refer to as red giants, are stars in evolutionary phases after the main sequence. So after the core has been depleted in hydrogen. So I've got my trusty Hertzsprung-Russell diagram for a typical globular cluster star on the right. I'm going to just block out that main sequence. And the evolutionary phases I was interested in or was studying was the red giant branch. Then the next stage is the horizontal branch. And then finally the asymptotic giant branch. I was looking at the start of the AGB, which I refer to as the early AGB. And these stars just haven't gone through thermal pulsing yet. So initially, globular clusters were thought to be simple stellar populations, which means that all the stars were the same age, the same metallicity, and the stars that we see today have very similar initial masses. But we now know that these globular clusters actually contain multiple populations which vary in light elemental abundances. So it's thought that all globular clusters contain typically 2 main subpopulations, sometimes more, and they vary in elements such as helium, oxygen, sodium, and so on. And the way that we usually can classify subpopulations is looking at that sodium-oxygen anticorrelation. So on the right, I show basically what is an observer's Hertzsprung-Russell diagram. We call it the color magnitude diagram. And the subpopulations are indicated by the colored triangles. In the inset, it's showing a sodium-oxygen abundance plot. You can see that the 2 subpopulations, and I should probably explain subpop 1, which is the first subpopulation, is typically lower in sodium and higher in oxygen, and subpop 2 is higher in sodium and lower in oxygen. So they can be clearly differentiated in that sodium and oxygen space. Something else I wanted to point out is globular clusters also show other chemical variations, and I recommend seeing Maddie Mackenzie's talk later to learn about that. So something else we know about from stellar evolution theory is that different initial helium abundances will result in mass differences between these subpopulations. So using that same notation of sp1 and sp2, sp1, which is lower in helium, will have higher masses, and sp2, which is higher in helium, will have lower masses. So if we look at the mass distribution, so looking at the masses within a cluster in each evolutionary phase, we expect to see a bimodality. So this is what I was trying to see within my mass sample. So how can we actually measure individual stellar masses? We can use something called astroseismology, which is the science of detecting oscillations that propagate within the interiors of stars. So I was looking at pressure modes or P modes. They're also referred to as acoustic waves or solar-like oscillations. And these are oscillations that propagate within the convective envelopes of stars. Astroseismic signals are described in terms of spherical harmonics and can be used to determine a wealth of knowledge about individual stars, where I was using them to measure really accurate seismic masses. And we can measure these masses by looking at the solar-like oscillations. So to measure solar-like oscillations, we take a Fourier transform of either a spectroscopic or a photometric light curve. And for main sequence stars and red giants, solar-like oscillations appear as these cone-like Gaussian-shaped structures. And I show an example of a solar-like oscillation for a main sequence star up on the top right. There's 2 global astroseismic parameters that we measure. The first one being Nmax, which is the frequency of the maximum acoustic power, and that's illustrated in purple. And the second one is delta nu, which is the large frequency spacing between adjacent overtone oscillation modes. To put that more simplistically, it is the frequency difference between peaks that have the same spherical harmonic L mode, and that's shown in the inset in red. Both of these parameters are correlated to stellar properties, Umax is related to the surface gravity and the temperature of the star, and delta nu is related to the density or the average density of the star. And if we combine that with the Stefan-Boltzmann luminosity law, then we can derive a seismic mass relation, which can be used to find the masses of individual stars. So I was looking at the cluster M80, which is relatively metal poor, and also faint, which means we can only look at bright RGB and early AGB stars. And the photometry for this cluster was from campaign 2 of the K2 mission, where K2 is the second photometric mission of the Kepler Space Telescope. M80 is only the second globular cluster that has detections of solar-like oscillations and measured seismic masses, where we have the first seismic analysis. And I ended up with a sample of 47 red giants. So how do we actually go search for this bimodality? So this is showing the mass distributions for both the RGB and early AGB evolutionary phases, and it's basically just a smoothed histogram. In our RGB, which is in red, we weren't able to detect a bimodality, so it's only singularly peaked. However, in contrast, for our early AGB, we clearly see 2 peaks, so we are detecting bimodal distribution, which is very exciting. And to analyze this further, we fit 2 Gaussians, and we take the means of the Gaussians as our subpopulation masses. We can further analyze this by comparing it to models. So Tylo and his team in 2020 produced subpopulation models for a collection of globular clusters, including M80. And I show his subpopulation masses after RGB mass loss in pink, and they are consistent within uncertainties with our values for the uncertainties other shaded regions. So this is an indication that we are detecting multiple populations, but we can't confirm that until we have spectroscopic measurements. So we need spectroscopic measurements of sodium and oxygen to actually classify our subsample into the subpopulations. But if we do see a correlation between subpopulation membership and our bimodal distribution, then this would be the first direct measurement of a mass difference between subpopulations. Something else that we can look at is the second parameter problem, which is referring to observed variation in horizontal branch morphologies between globular clusters. And I show a typical example of 2 clusters, M3 and M13. I've highlighted their horizontal branches in the pink boxes. As you can see, they are very different. So metallicity can partially describe these variations in horizontal branches, but we require a second parameter or parameters to fully describe why we see these variations. So in that same Tylo study, he proposed 2 second parameters, the first one being helium abundance variations, which is just referring to the multiple populations. And the second one is differing RGB mass loss rates. So we were trying to test that by seeing if there is a difference in the integrated mass losses between subpopulations. So I'm going to go back to this one plot. And the first thing we needed to do was find the mass loss, the masses on the subpopulation masses on the RGB. We found those from models. We found quite a small mass loss difference from models. Mass difference from models, which does explain why we're only detecting a single peak in our RGB distribution. To find integrated mass losses, we find the difference between evolutionary phase masses for each subpopulation. And that is illustrated by those arrows. And one thing you'll notice is for the second subpopulation, which is on the left, these stars are losing a considerable amount more mass than our subpopulation 1 stars. This is again in agreement with the Tylo models, and also the absolute values of our mass loss or integrated mass loss values are also consistent with Tylo's results. Again, we can't confirm this until we have those spectroscopic measurements though. So just in summary, this is the first seismic analysis of the globular cluster M80. We have a possible detection of a mass difference between subpopulations, which could be the first direct measurement of this. And finally, we see evidence of mass loss differences between the subpopulations, which could inform the second parameter problem. Thank you.